So we are in the last week of QFT2, and we're gonna have the two lectures on large N. We've had discussions of large N here and there. For example, where we discussed the Wilson-Fisher fixed point. Wilson-Fisher fixed point as epsilon was going to 1. So we could find the d equals 3 fixed point perturbatively under RG. Under some perturbative RG flow, we could find the fixed point in 3 dimensions or 2 dimensions if we have large N, right? Because beta function had 1 over n suppression. But today we're gonna discuss that, and that was a global symmetry large N, right? So today we're going to discuss large N and its consequences for gauge theories in a little bit more systematic way. As usual, I'm going to start with this review of lecture 27, the theta term and quantization and instanton. So if you have any questions from the last lecture, please ask as we go through this. So to start, remember how we introduce gauge theory and how we introduced gauge theory in QFT1. Gauge theories were theories that had some intrinsic non-locality that we said has topological flavor, and because locality was so important for us, we insisted on local description. We ended up with description that was local, but then there were redundancies. So what is this non-locality we're talking about? The manifestation of this non-locality is a Wilson loop that goes around that, circles some flux. So the magnetic flux inside is non-zero, so it's perpendicular to the direction of the orthogonal to the surface of the loop. So there's flux going through the loop, but we, for example, make sure that the solenoid or whatever it is protecting the magnetic field so that at every point around the loop, B is 0, right? So equations of motion, the physical gauge invariant observable was B, F mu nu, B and E, right? Which means that at every point, there should be no magnetic field or electric field. However, we know that the integral, the Wilson loop, the integral over of A around the loop by Stokes' theorem has to be the surface integral of B. Because there's some flux going through it, it means that this integral cannot be 0. The only way to reconcile this is to say that there's a gauge transformation. So A mu is pure gauge at every point, but the gauge transformation is non-trivial. As you go around the loop, the gauge transformation is this large gauge transformation that's not single value. So you go around and come, just topological non-trivial. So these Wilson loops were new non-local observables of the theory, and the word topological has to do with flux quantization. So that is a quantum mechanical. Is that clear? I'm going to comment on this in a bit. Yeah. So even though at every point the magnetic flux is B, but there's this topologically non-trivial gauge transformation that we're dealing with. Now, of course, the classical equations of motion only CF mu nu because they're local, but quantum mechanically, so classically there are no consequences, but quantum mechanically, we saw that in QFT1, we saw that there's a Aharonov-Bohm effect, which says that as you go around the loop, as you carry a charged particle around the loop, you pick a phase shift in the wave function. Now, a global phase shift in the wave function, is not observable, but the relative phase is. So if you have two particles that you send, a particle that you send this way, a particle that you send this way. Now the phase shift is understood. This loop phase shift is understood as a difference and the phase that you acquire as you go along this path and this path, right? And that has to do with, if you recall from the geometric description of gauge theory, it has to do with the curvature, which is F mu, right? All right. So quantum mechanically, this topologically non-trivial gauge configuration has no classical consequence, but quantum mechanically it has at least observables. More generally, topologically non-trivial field configurations in Euclidean spacetime are called instantons. So I say Euclidean, but like for simplicity, imagine that you use gauge transformation to put A0 equals 0. So you're only dealing with R3, right? And because, as we were just saying, if you require that the gauge transformation trivial at infinity, you're basically dealing with S3 because you can take that as a point, add that as a point. So what you learn is that these these large non-trivial field gauge transformation or field configurations, these instantons, they do not have any, they do not teach us any, did not appear in classical physics, but they appear in quantum mechanics and lead to important changes in the quantum description. Yes.
What do you mean by they don't appear in classical?
Meaning, meaning that classical physics, right, cares about classical equation of motion. That's all. Classical equation of motion. I shouldn't say, yeah, I think I should be careful with this statement, right? Because you could discuss gauge theory even in classical gauge theory, right? But by classical, I mean equations of motion, classical equations of motion. Because we saw that instantons are actually solutions to the classical equations of motion. Euclidean classical equations of motion as well. Good. Any questions?
Actually, no, actually, what you mean, they're not relevant. Classical.
They are invisible to the local classical equations of motion. Think about this loop, some flux going through, right? Equations of motion are local. So they only see B, F mu nu. The right-hand side of equation is a solution that enters the differential equation F mu nu, right? F mu nu is 0, of course. So classical equations of motion miss this completely. Now, once you've introduced the gauge principle, we realize that these have to do with non-trivial gauge transformations. Good. Yeah, I think that the term classical is a little bit misguided. It's more local equations as opposed to global properties.
Because you would still something like this in like classical field theory, right? Like classical.
Yeah, that's the thing. So local physics doesn't.
We're talking about like not a field theory, like you're solving electron motion pointwise.
Yeah. All right. So we said that this is intimately tied to the theta term. For example, in D equal 4, consider the theta term. Consider Maxwell theory. Einstein, sorry, not Einstein. Maxwell theory is just F mu nu squared, the standard Maxwell equations, and you could write this down as an integral over E squared plus B squared, and the usual gauge a not equal to 0. Now you could define a dual tensor field strength, which basically is like F mu nu with E swap with B with an extra sign. So E goes to B and B goes to minus E. So now you could add to the action a term that is E dot B, and that is star F mu nu F mu nu, right? More generally, when you have a non-abelian gauge theory, the term that you add is star F mu nu, but there's a trace, right? So these are Lie algebra values, hopefully you recall. So here, even though I don't put any indices, but these are all Lie algebra values. This, I only put space-time index, right? Not the Lie algebra index. So you could define the non-abelian electric field to non-abelian magnetic field, but recall that these are not gauge invariant. When they're in the non-abelian theory, F mu nu is not gauge invariant. Lagrangian is 1 over g squared with the appropriate scaling of the gauge field. A dot squared minus b squared. So here A dot is really E squared, E, right? And then there's E dot B, but the non-abelian version thereof that plays the role of the theta term. Gauss's law basically tells is very similar, works similarly in non-abelian gauge theory. It's a constraint on all physical states. Now there's a conjugate momentum, and written in term, so the Hamiltonian could be still written as trace of E squared plus B squared. But now the important thing is that in the presence of the theta term, the conjugate, the conjugate momentum is momentum conjugate is not just E. It's actually, it has a theta term added to it. So when you canonically quantize, what this is to understood is, the way you can understand this is that this is just a free theory, but with a changed deformed Poisson bracket, right? Now, we don't have time to get too much into the details of what the consequences of this are, but just to say how it works, think about this Hamiltonian trying to solve Schrodinger equation for this model, right? In the observation was that in the presence of the theta term, so there's this extra theta term. In the absence of the theta term, if you find psi naught solutions, then you can write down the solutions for the case with the theta term, right? So if psi naught is a solution with theta equals 0, then psi theta is just psi naught multiplied by this functional of A. A to the power of I theta functional of A. This functional is nothing but the Chern-Simons functional. Good. So this Chern-Simons functional had some interesting features. Well, it satisfies a constraint as well. So you could check explicitly. But importantly, this Chern-Simons functional is not gauge invariant under topologically non-trivial gauge transformation. Under topologically non-trivial gauge transformation, it is shifted by an integer. It's shifted by an integer, which means that the wave function is shifted by this phase. Right? So this is the same extra phase we talked about when we were talking about the Bolmar. Similar, not same, similar spirit. Good. For example, consider R3 under gauge transformation, and non-abelian gauge transformation takes this form. And under this for such a generic case of a pure gauge transformation, then W of A, the Chern-Simons term, changes this way. This is a total derivative term that you push to the boundary. You deal with it the usual way that you deal with this term. But this extra bit is the piece that becomes an integer. Notice that this extra bit is absent in the abelian theory. So I briefly commented for you guys, if you're interested to go learn more about this, that this winding mode that we're discussing, these non-trivial topology, non-trivial gauge transformations, can be understood as maps from S3, 3-sphere to group G, and this is Z, basically, pi 3 of G. All right. Now, we said that there was So we said that we could use the dual field as a trick to generate solutions to the classical equations of motion. So classical equations of motion are second order equations, right? But as we'll show right now, if there is a field configuration that's self-dual, it will solve the classical equations of motion. But the self-duality condition is first order, so it's easier to solve. Do you remember why it solves the differential equations of motion?
Yeah, okay.
Bianchi identity. Right, because d star of f, sorry, d of f is 0, that's Bianchi identity. If f is related to star f, then that equation gives you d star of f is 0, which is the Maxwell equations. So we said this, but we said that in the fancier terms, we took the Yang-Mills action, added and subtracted this term, and then we know that this is an integer, right? So we instantly said that this has to be larger or equal to 4 pi squared over g squared that. Sorry, I just said something. Yeah, no, that's correct. Because this term is this is positive. These solutions are called instantons. Yeah, they're the instantons. That were interesting. All right. So this is a review of the lecture from last week. There's a lot of literature out there on the Chern-Simons theory, about the theta angle, about when you make theta space-time dependent, the axion field, the phenomenology of axion field. So there's a huge literature out there, and it's an interesting area of research. I just want you guys to have seen this. Any questions before we move on to large N theories?
Very compact, if I ask you, you always treat infinity together as a single point, right? Why do you do that? Why not take infinity bigger space?
Like, so yeah, like what?
Okay, so I just say what I think intuitively.
So whatever infinity of space is, we want omega to take the value 1 there. Now, when you're talking about your gauge field, it's a map that the freedom of which the map is from R3 to D, but it always have to take the same value 1 at infinity. So you can treat it as a point. Right? As a map, you could treat it as a point. Because you're just interested in classifying the maps. Right? Take a map from S3 to G, right? And just say that the value of that at a point that you're mapping to infinity is not just 1 point, but it's at every point in space-time. It doesn't matter. Because you're looking for field configurations with the constraint that infinity is always 1. Right? All right, yeah.
Yeah, okay, so looking at Aharonov bone, so like in Aharonov bone, we don't have the theta term, right? But it feels like we get something similar in that you still have like your momentum still shifts because of the vector potential is there. But is this like, that's what I'm saying, is Aharonov bone like a little different than this because we're in 2D instead of.
Yeah, so yeah, very good. So there's an Aharonov poem that you know what it is, right? It's a map from S1 to G. So it deals with the pi 1. I gave you an example of a setup where we're dealing with pi 2 of G. This was when you had a magnetic monopole, right?
Yeah.
In the magnetic monopole, what we ended up with was a topologically non-trivial S1 fiber on S2. So this was the magnetic. There was the magnetic monopole here, right? Magnetic monopole G. And then we took the S2. We have a U1 gauge field. So that's like an S1 at every point. And the field configuration that gave us A mu corresponded to a non-trivial topological set here on this S2. right? So that was an example, one-dimensional higher example. But in general, these instantons are just three-dimensional things. They're there could be any, right? So these, I know that I didn't answer your question, but when you're talking about I'm just making a connection between a phenomenon that you already know, which is the fact that there could be physics, there is brand new physics associated with topological non-trivial gauge transformations on S1, on S2, but now I'm saying on S3 as well. But right, they exist. There are such field configuration, they exist, they contribute to the quantum theory, but I didn't explain it in terms of some sort of Stokes theorem or anything. Right?
So we don't need the theta term always for these like
Yeah.
topological things. Theta gives us something very interesting.
Correct. So the coefficient of the theta term is topological.
Yeah.
Right. Good. All right. So let's change gears and talk about large N perturbation theory. Quantum field theory at the large N simplifies, and I'm going to argue for 1/n perturbation theory, treating 1/n as a small parameter. So just to have something in mind to hold on to, if you have the standard path interval d of phi minus s of phi over h bar, or I s of phi over h bar. The fact that h bar is small allows you to organize the perturbation theory. So 1/h bar is a large number that enforces saddle point approximation or stationary phase approximation and Lorentz density. Now, if you have the same thing, but you want to keep track of quantum effects, you don't want to suppress quantum effects. But using another technique is that if you have another parameter n sitting outside that is large. Now, this n being large gives you quantum theory, because this is the h bar of your theory, right? But you can still use saddle point like approximation and perturbation theory. So this is the very, very high level idea behind 1/n expansion. Very high level idea behind. And you will see that always in your Hamiltonian action, you normalize such that n sits outside as an external parameter. Yeah.
When you say n out, it is always the number of fields or something like that, or that n mean different?
So if you have n different fields, for example, in the ON model or in like SUN, as we'll see, that will be a natural candidate. But for whatever reason, any parameter that sits here will play that role, right? Here, if it's a number of fields or n is some integer, so that's the set that we're talking about. I'll give you an example where from quantum mechanics, where this n is dimensionality of space-time, some integer. All right, now the general intuition, we have very limited time, we have only 2 lectures, but let me give you the general intuition and you can go read about them. We said that two ways that we've talked about sensible interacting theories are, these are either global symmetries, like the ON model, or these are gauge theories. Both of them have this n parameter, there's symmetry principle at work. So in the case of global symmetry, the number of degrees of freedom typically scales with n. These models are solvable often. Examples for you to learn is CPN -1 or Gross-Novo model. If we have time next on Thursday, I'll go through I'll make some comments about this. I doubt that we have time. But because we have discussed certain 1/n large n aspects of global theories, and we haven't touched 1/n large n properties of gauge theories, today I'm going to focus on gauge theories. So in Yang-Mills, these are setups where the number of degrees of freedom scale like n squared. right? These models simplify, but they remain unsolvable. That's what makes them interesting. They will be related to gravity and such, yeah.
What do you mean solver again?
Solvable means that I can just integrate them out, write down the endpoint functions explicitly. So, pressing issue question that comes up. Can this be used for QCD? Where n is 3. So 1 over n squared is 1 over 9. Is it large enough? So here's a story from my own life. I think 1 over 9 is large. For the following reason. Well, first of all, 1 over 10 in perturbation theory is counting significant digits. That's good. But the other reason is that every time I go to the gym, I run 1 kilometer to warm up. I recently, just actually this Saturday, I did 10K and killed me. So 10 is a large number. 10K is a lot of Ks. So you could test this yourself. 10 is a large number. All right. But here we're talking about asymptotics, right? All right, so an example from quantum mechanics to just warm up a little bit, how large n could be used to simplify things. Imagine so what we're gonna do is we're gonna solve the hydrogen atom, that whole annoying section of quantum mechanics, whether it's Griffith or whatever textbook you took, of a lesson on PDEs, without solving it. We're gonna approximate it without solving it, based on the idea that 3 is a large number. So here's a Hamiltonian, right? Remember that alpha is squared over 4 pi. So as usual, the first step of this is to write everything in dimensionless coordinates. So here it is. We redefine everything to r prime, and this is what the Laplacian becomes. This is what the Hamiltonian becomes, and this is the unit of time, right? The dimension full parameter that sits outside of Hamiltonian. Like is the thing that sets the dimension of Hamiltonian tells you about units of time, how you measure time. Naively, well, what is this number? It's alpha m squared. So naively, when you solve the equations of the Schrodinger equation, what comes out of it, this dimensionless Schrodinger equation, what comes out of it is some order 1 numbers, right? Because there's no reason for large or small numbers to produce. So naively, you expect the atomic energy scale that appear in this problem to be order m alpha squared. That is 27.2 eV. That gets the correct answer by factor of 2 without solving anything. So solving the Schrodinger equation, all that work you went through just gives you a factor of 1 over 2, right? If you lived long time ago and you just wanted to know, like you didn't want to solve any differential equations, you want to know what is the ballpark, like what's the energy scale, you could get it right by factor of 2. 27.2 eV. All right, so we want to do a little bit more. What is the large n parameter here? We're going to treat the dimensionality of space-time as a parameter. Now, in higher dimensions, Coulomb law will be modified. But because we're interested in setting up the perturbation theory, similar to what we did in dimension dim reg, we're going to keep the 1 over r squared law, but change the dimensionality of space because we're going to build the perturbation theory around the equal theory. So we're going to keep the Coulomb force, or not Coulomb force. Yeah, let me put r squared. We're going to keep the Coulomb force as 1 over r squared, the Coulomb potential as 1 over r, right? And solve in n dimensions. So here's the equation. This is the Laplacian. Now, first thing you notice that when n is large, n minus 1 is the same thing as n. So I could just suppress that. Then you make the following redefinition, the redefinition of the wave function, and you define this new radial variable. This is what your differential equation becomes. Why do you do that? So that you want to take n out of the equations. Right? That's the whole goal. You want to write down the final equation as some constant, some parameter that could be independent, multiplied by this differential equation, which has no n in it, times chi is E chi. Right? Because I can eat this into the definition of E, and now I have an n independent differential equation. Right? Sorry, I said something wrong. No, I said something wrong. You want to take the independence out of the potential. The independence ends up next to the kinetic term as the mass term. Right? For a massive particle, this is dr squared, d squared over dr squared, 1 over 2m. So n squared plays the role of m, mass. Now, large n means a heavy particle. As I said, you're a lazy person. You don't want to solve the differential equation. You just want to guess the answer. When you're trying to solve differential equation, you're trying to solve Schrodinger equation for a very heavy particle. What do you find? You just find the classical physics, right? Because the particle is very heavy. So what happens is that you basically replace all of this stuff with the minimum of the potential, right? And the ground state energy is going to be this parameter times the minimum of the potential. That gives you m alpha squared over n squared times 2 plus, that is incorrect. One over n corrections. So this gives you 2m alpha squared over 9 in 3 dimensions. The correct answer is m alpha squared over 2. Again, you're off by a factor like 2. Not 2 exactly, but almost. Right? So this is the basic idea. But we're going to do it a lot more systematically. Good? All right. Large and Yang mills. So let's remind ourselves of the role of large n, and let's figure out what is the large n limit. So as I said here, you're sending n to infinity, right? Keeping h bar fixed. In the past, when we talked about gauge theory, we ate h bar into the coupling of the theory, right? So what is the right approximation? Do you want to send n to infinity keeping g fixed, or do you want another limit? That's what we're going to discuss now. Good? All right. If you do send n to infinity keeping g fixed, you do not get the physics that's the most exciting. Why is that? So we're going to go through that. Is it clear what I'm going to explain now? So we're going to define a parameter. We're going to take the following limit, n to infinity, g to 0, such that n g squared called lambda to coupling is kept fixed. So I'll explain this. Why we take this limit for gauge theories. So S-Yang, let's just take pure Yang mills, right? Pure gluons, no matter. Next lecture, we're going to talk about adding matter. We're going to talk about QCD. So this is minus 2 over g squared. I think in the past I was using 4. Doesn't matter. 2? No, 2. I forget. Yeah, that's right. Yeah. So here it is. So what was the beta function of this theory? We calculated the beta function. It was minus 11 over 3, 1 over 4 pi squared, the one loop beta function, C2 of g, g cubed. We did this in several different ways. We did this calculation in several different ways. And we found that this is precisely, this minus sign is precisely asymptotic freedom. Starting at g squared delta uv, some subcoupling at uv, as you reduce the scale to mu, the coupling grows. It's a relevant deformation. How does it, if you solve it, you find that the coupling g squared of mu at the one, using the beta function, one loop beta function, it naively blows up at some lambda, that's called lambda QCD. So there's a naive Landau pole well, there's a Landau rule. Landau rule is a naive thing, right? The one loop analysis tells you that at this scale, it blows up. What is the scale that blows up? It's 1 over lambda uv e to the power 1 over 2 beta naught g squared. Beta naught is this. You put in everything, you get lambda uv e to minus 3 over 22 4 pi squared g squared n. Okay? Now, do you see what the problem is? If I send n to infinity, keeping g fixed, I find that the theory is infinitely coupled at the cutoff, right? So that's not a good limit. That naive limit is not a good limit. So this story that I told was a little bit too naive. It's still, the principle is the same. I'm going to organize my theory, as you can see in a second. I'm going to organize everything such that the thing that sits outside is large, and I take a large n limit, and everything is organized properly, right? So what is the limit? Based on this, what is the limit that you want to take? If you don't want to, if you want to, for example, use large n approximation to learn about QCD, you want to take a limit that doesn't change lambda QCD. That's the limit that n goes to infinity, g goes to 0, such that g squared n is kept finite. So that lambda QCD over lambda uv is fixed. Otherwise, the whole physics is going to get messed up. Right? That is the origin of definition of the 't Hooft couplings. This was Tooft's observation back in the 60s. Right? Sorry, I think so now you see what's going on. In non-abelian gauge theory, you don't have an n in front. You have the non-abelian gauge action here divided by g squared. Because you define lambda is g squared over n, that corresponds to n over lambda outside. You're taking lambda, 't Hooft coupling, to be order 1, sending n to infinity. Right? So it is sort of the story that I told before, except that now h bar is hidden in lambda. And that's how I brought that out an n. Good? So this form is very important. We're going to take, every time we're talking about large n limit, so here's where the distinction between global symmetry and gauge theory is. Or I shouldn't say global versus gauge. I should say these are adjoint representation, adjoint gauge fields, as opposed to things that transform in fundamental representation, like ON model. The distinction lies in precisely this, that in this case, what is natural is this 't Hooft coupling limit. In that case, if you study it, you will see that there's a little bit of different scaling of parameters. That's relevant, right? This analysis is very much tuned to Yang-Mills. Any questions? So now a lot of things happen at large n. So in non-abelian gauge theory, we said that the gauge field is Lie algebra valued. It's a SUN Lie algebra. So how many generators are there? N squared minus 1. So I can think of this as a matrix, right? So these are my gluons. Of course, if I think of these as matrices, I don't have 9 degrees of freedom. I have 8 degrees of freedom. That's obvious from the fact that when you look at the 2-point function, you get the structure. These guys are orthogonal. But there is this mixing term, which is 1 over n. This has to do with the tracelessness condition of SUN. If you did UN, you would exactly find that you could just treat these guys as independent. Now, in large n, the distinction between UN and SUN goes away. You could just drop this. This is the origin of the so-called double line notation. So at large N, you could view SUN theory as UN theory pretty much, and then you could view these guys as matrices, as, so you should have mu A, mu B. This you could view as like a two lines. Each transforming, one is transforming in anti-fundamental, the other one in fundamental. If you recall in QFT1, at some point I described how the adjoint representation could be thought of as a combination of fundamental and anti-fundamental as well. There was a discussion of that. If you go back to those notes that I learned, you cannot open anymore. I'll have to fix that.
QFT two things are working though now.
What's that?
Lectures for QFT two are opening up.
The early ones?
I've done nothing.
I just checked right now and they're opening
That's
up.
so weird.
The
This,
Early ones are there.
this is, yeah.
Apart from the latest.
Bill Gates is messing
So
up.
apart from lecture 27, the previous one.
Oh, because no, I have not posted that.
Okay.
I just posted it before coming to class.
I just checked it right now and it's saying a request a verification code.
Oh my God. All right.
But anyways,
Anyway, so this is the origin of the double line notation. You can check later, it's all right. Now, here's an important exercise for you guys. I absolutely recommend that you do it because you should see how these work. So let me just write on the board what I'm asking you guys to do. So S Yang Mills is n squared over lambda, or 2 lambda, doesn't matter. Integral of d4x trace of f mu, right? Remember the definition of the covariant derivative? All of that. Derive the Feynman rules for this theory. There is a propagator, there is a 3-point vertex, 4-point vertex, right? So what I want you guys to derive is just go and do the standard Feynman derivation of Feynman diagrams. You'll see that every propagator comes with a factor of lambda over n. That's not too hard to see. Oh, sorry, it's not squared. It's that. It's just because it's a normalization of that. But every 3-point vertex and 4-point vertex come with the inverse of that, n over lambda. That's a little bit more counterintuitive. But it's just Feynman diagram. You just literally push this through. So this is not something that you haven't perhaps seen, where the vertex is inversely proportional to your coupling. But it's an artifact of the change of variables you've done. But it's important because the whole counting of Feynman diagrams and the whole like summation of the perturbation theory here relies on those coefficients. I know that we don't have any more homework to do for deduction, but it's good to do if you want to, if you feel so inclined. All right. A general diagram will have a bunch of propagators. Every propagator comes with a factor of lambda over n. A bunch of vertices, they come with negative powers of lambda over n. And every loop comes with a number of index contractions. Right? But these are index contraction in the double line notation. So for example, if you have this, vacuum bubble, if you have this vacuum bubble, right? So how does this work? You have one propagator that's lambda over n, and you have n squared because you have 2 of these loop index contractions. This is lambda. Let's look at this guy. How many propagators are there here? 3. So it's lambda n to the power of 3. There are 2 vertices. That's -2 and then n cubed. Because there's 1, 2, 3 index contractions. That's lambda n squared. Now, what was important in this, part of the magic of this is that you don't need to distinguish between 3-point function and 4-point function. They come with the same scaling. So that's why I want you guys to do the calculation, do this derivation to see that they come with the same. It's a trivial, it's absolutely trivial. Okay? Let's look at this guy. These are all bubble diagrams, right? This is lambda over n to the power of 6 because there are 6 propagators, right? 1, 2, 3, 4, 5, 6. There are 4 vertices, 1, 2, 3, 4. They're all 3-point vertices, but it doesn't matter. So that's lambda n to the power of -4. And then there's n4 because 1, 2, 3, 4 loop indices. Index loops. That adds up to lambda squared over n squared. So what we're doing is we're keeping lambda fixed and taking large n. So this is important, and they appear in the same order. N is the large parameter, or lambda is whatever. Now consider this contribution. It's non-planar, right? You cannot draw it on a plane. Is it clear what I'm drawing here? Right, so this is like analogous to this diagram, except that the inner one is contracted with the outer side. That's why I've drawn it this way. So let's see. How many propagators are there here? There are 3 of them. How many vertices are there? There are 2 of them. So far it's like this, but then there's only 1 index contraction. Just follow a line. See where it goes. This add up to lambda is 1 over n squared suppressed. So you discard that diagram. This is called a planar, non-planar diagram as opposed to the other ones. Planar means you could draw it on a plane. Non-planar means that you have to do this funky thing. So it cannot be drawn on a plane. This was showing the basic logic, but the idea is that planar at large n, planar diagrams are all the same order n squared. Non-planar diagrams are n squared suppressed. So you throw out all the non-planar diagrams. Of course, the planar diagrams include arbitrary higher point function higher loops. That's the sense in which they're quantum mechanical, right? But there is another form of suppression imposed by 1 over n. This is, by the way, at the heart of string theory. This whole perturbative expansion is really where string theory lies. But anyway, this intimately tied to the birth of string theory. But we're not talking that. We're talking SUN. So planar diagrams are those that could be drawn on a sphere. Right? Here's an example. Non-planar diagrams need higher genus surfaces, 2D surfaces. For example, torus is the way you draw this guy. So there will be torus is genus 1, genus 2, and so on and so forth. The number of, so you could think of these Feynman diagrams that we're drawing as tessellation of these Riemann surfaces. So triangulation or tessellations of these Riemann surfaces. Number of edges become number of propagators. Number of faces is the number of index loops, and vertices are vertices. In our diagrams, we saw that the counting went this way: lambda over n to the power of e number of propagators minus the number of vertices n to the power of f. That means that n is to the power of f minus e plus v. That has a name. That's called the Euler character. That is precise and it's topological. It's independent. It only depends on the Riemann surface. That's precisely why we're getting 1 over n suppression, 1 over n squared suppression, or sorry, 1 over n squared suppressions for higher Euler character, higher genus surfaces. Planar ones are the only ones that survive. Now, also, you immediately learn, yeah, and you don't care about the power of lambda. This is non-topological, but it doesn't matter because lambda is order 1. This also gives you principle for 1 over n expansion, right? If you want to go to 1 over n squared order, what do you have to consider? All the Feynman diagrams that could be put on surface of a torus. We go to 1 over 4 n to the power 4 genus 2 surface. This is string perturbation theory. So it's an expansion in the topology of the diagram. Any questions?
How do you simplify it? And till now, all the diagrams have been drawing like Feynman diagrams, technically you're drawing them on a plane, and that's complicated enough. So how does introducing non-plane diagrams make life?
Well, I'll give you examples. There are a lot of it. Well, I'll say actually on the next slide. Yes, I'll say on the next slide how it simplifies. It does. Believe me, it does. It's not solvable. It doesn't make the theory solvable, but it simplifies. So here's the answer to a question. Large n limit is classical. You shouldn't be surprised, right? Because I said that it comes from some saddle point approximation, right? So solving the quantum equations become finding the saddle to some classical equation. But I'm going to describe it a little bit differently. What are the gauge invariant observables of Yang mills? They have to be color singlet. They have to be traces. What's the operator that you have? So you have F mu nu, that's a physical observable, but it's not gauge invariant, right? So you have to consider F mu nu A, F mu nu A, right? Sum over. This is, let's schematically write a trace of F squared. You could have F mu nu F rho sigma at point X trace. This is gauge invariant. This is a composite operator, right? So it will have a renormalized scaling dimension. We'll have all of that, right? In fact, these are called single trace operators for obvious reasons, because they have a single trace. In general, there will be multi-trace operators also as gauge invariant operators. But notice that these single trace operators generate an algebra that include all the multi-trace operators. So if you want to look at the fundamental objects, you have to look at single trace operators. They are like particles. So multi-trace operators are multi-particle states. We'll see that literally holds at large n. But importantly, trace of F squared and trace of F4 are not related at large n. At large n, they're actually independent. Of course, you're not allowed to take trace of so many Fs that becomes order n. If you do that, this is no longer independent. If you guys know about free probability theory, I'm describing to you what free independence is. But said in the language of field theory as you know it so far, in the large n limit, we're going to be dealing with this trace of phi mu nu k's. Right? These are single trace operators, and we're going to treat them as sources. We want to calculate the endpoint functions of these guys. That's what we want to calculate. So we're going to add a source like that to the action. We calculate that we know that the connected piece of the correlator is 1 over np squared. This is the proper normalization, a bunch of derivatives, log z. Remember that the log of the partition function was the generating function for the connected correlators. So you do the n counting, you find this amazing thing, which is if S has an explicit n outside and no n inside it explicitly, log of z is order n squared, and the endpoint connected function is n squared minus p. So what does that say? That says that in the strict n going to infinity limit, the theory is Gaussian. Each of these trace of f to the power of k's, right, is independent of the other guys. They have 2-point functions, but the connected part of higher point functions are 0. There is Wick's theorem at work, roughly speaking. It's not Wick's theorem, really. It's similar, right? The connected part of the correlators vanish. 2-point function fixes it all. This is called generalized free fields. There is some notion of Wick's theorem, but right? So the theory is free in a sense. It's interacting, but if you view in the strict large n, there is another way of organizing degrees of freedom where it looks free. That shouldn't surprise you at all. In the saddle point approximation, what you're doing is that you're replacing the path integral by Gaussian, right? So now the standard perturbation around this Gaussian is not the old perturbation in 1 over h bar. So the notion of your excitations are different. But with respect to this, everything looks like there are these trace of f to the power of k are in new particles. Any questions? I know that I'm going through this very, very fast. But again, this is the end of QFT2, and I want you guys to have seen this and be able to follow it later. Now, let me make a cryptic comment. We'll come back to this hopefully in the next lecture. If at large n, if the theory confines and has a mass gap, each single trace operator is a particle. Do you guys know what I'm talking about?
What's the mass gap?
Mass gap means that there's vacuum and the first excitation has a
Is mass.
mass.
Okay.
So remember, sorry, one thing. In the scale, in the tooth coupling large n, so we kept tooth coupling order 1, whatever, and we took the large n parameter. We intentionally did this so that lambda QCD is unchanged. Confinement in non-abelian gauge theories was a statement about the degrees of freedom below lambda QCD, right? Versus above lambda QCD, right? Below lambda QCD, confinement told you that everything had to be singlet, right? And your entropy, your counting of the degrees of freedom was different. This is referring to that. Now, in next lecture, I think this is the end of my slides for today. In the next lecture, I will go through a more detailed discussion of large n and gauge theories, and we'll build mesons. We'll build a theory of baryons. We'll discuss all of that. So unfortunately, large n approximation is not enough to explain confinement. It can't give us a derivation of confinement, but it can still teach us a lot about the theory, the spectrum of the theory. Right, good. So in summary, let's rewind. I think we'd seen in the past that large n approximation in global symmetry was a useful technique for example, in Wilson-Fisher for getting perturbatively accessible IR fixed points, IR fixed points, right? Today we discuss large n and gauge theories. Even though I didn't discuss large n and global symmetry today, at the beginning I made a disclaimer that the story is a little bit different. Those models, large n models for global symmetries, often lead to integrable models. you could solve them just directly. This is intuition. It's not literal. If you don't come to me, say, here's an example, counter example to what you said, right? If you come, yeah, actually do come. But then the non-abelian version, sorry, the gauge theory version is a little bit different. The number of degrees of freedom is order n squared, right? And in this setup, the theory becomes classical but solvable. It's not solvable, typically not solvable, right? An important thing that we said today was that to make sense of this limit, we want the gap, the distinction on energy scale between lambda QCD, where the theory becomes strongly coupled, and the cutoff to remain meaningful. We don't want the beta functions to change drastically, right? For that reason, we take the tooth limit. This is n going to infinity, g going to 0, such that g squared n, which is lambda, tooth coupling is kept finite. Because of that, we write the S Yang-Mills as n over lambda. Now there's this explicit n sitting outside, so large n enforces saddle point or stationary wave approximation, right? The Gaussian part of it will tell us that if you look at gauge invariant observables, which are signal trace operators, the connected piece of the endpoint functions will vanish, right? For any Gaussian probability measure, that's true. Is that clear? Yeah. Okay. Wait, I said something incorrect. I said something incorrect, yes. I take those words back. Yeah, here the connected piece vanishes. Well, what I said is correct, but there is some subtlety, but I don't want to confuse you guys. All right. Any questions? We'll discuss this in more detail next time. But any questions? Pure Yang-Mills, yes. Very good question. What are the excitations of pure Yang-Mills? Below, so gluons will be the excitations when the theory is not asymptotically free. It will have to be above the lambda QCD, but below it, you're gonna end up with, yeah, gluons. Exactly. So these are a combination of a bunch of gluons. Now, the theory is very, very complicated still. We're gonna discuss the case of QCD, which means that matter coupled to Yang-Mills, to discuss mesons and baryons, right? That's a natural setup to consider. Any other questions?
So the other thing was, so we were discussing the you mentioned that it's inversely proportional. Yeah, it's inversely proportional to count. This is not. But again, even at like 5 4.
Sorry. Lambda over n, n over lambda. Lambda over n is the propagator.
I mean,
Inversely proportional to coupling lambda, yes.
but that is true, you want to say 5 4. But the coefficients in the action is 3 factors, the factor which comes in.
No, and sorry, let me try to explain what I mean. It's nothing magical. But remember in the standard notation where we had -1 over 4 raised to f, well, let's take it to be just like QD, right? So this was del mu A minus no, sorry, that's not what I wanted to do. Yeah, no, I absolutely have to take the non-abelian one, because I want the vertices, right? So here in D mu, we had A mu, E mu minus I, E, G, right? What was that? A, B. Right, so this is A, right? Which tells you that your propagator, Coulomb propagator, is going to be mu A, mu B. Your three vertex will come with a factor of G. And four vertex will come with a factor of G squared. So these are small and suppressed. Right? So all I'm saying is that, and now your propagator is order one. If you redefine A to GA, your propagator is going to be 1 over G squared. Right? This guy is going to be wait, what? So this is going to be G cube A cube 1 over G squared. Right? Is that right? Yeah, that's correct. So it's going to be 1 over G squared. And this guy is going to be 1 over G squared. Take 4. Now you put. Right? This is not quite correct. This analysis is not quite correct because you're removing the 1 point function. You're removing the connect. These are connected pieces. So let me not actually say this. Yeah, let me not. So 1 over G squared, and here's obvious. Right? But what the point I was making before is actually, let's forget about this. We usually say that these guys are suppressed by the power of the coupling. So therefore, we organize our perturbation theory this way. Here we are rearrange something. Let's say you want to do perturbation theory in small lambda. Right? But here it's kind of weird because it's 1 over lambda. What I was saying is just it looks a little bit different from what you're familiar. Actually, I think I messed up here. There's a one liner to see that these guys are gonna be, yeah. All right, any other questions? At the end of the day, I guess the lesson is that saddle point approximation, mean field approximation, stationary wave approximation, they're all the same thing. As one of the basic tools we have in physics. Yeah. And large N, often the theory is classical, but there are H bar terms. So it's not classical, like it's not, the theory has a bunch of saddles, but they're not, it's not classical field. Sorry, it's classical field theory, but not in 1 over H bar. This is the origin of gauge gravity dualities, right? So the boundary theory is horribly quantum mechanical, but there's some sort of classical picture that comes out. All right. Anything else?
Well, what is the mixing term look like again?
Mixing term.
The
Connected.
fundamental anti-. In the propagator.
This guy?
Rather, yeah.
This. Is that what you mean?
Yeah,
The 2 point function? Yeah, so the 2 point function looks like this, which looks like fundamental and the fundamental.
yeah.
I think I got the arrows correct, I don't know.
Oh, yeah.
And then there's 1 over N. This 1 over N has to do with tracelessness. Yeah. Now, I mean, if you think about it, the trace is 1 degree of freedom, right? And N squared of it. So at large N, it doesn't really matter. But once you start doing perturbation theory, you got to be careful with this, right? But now there are corrections that come from this that will be comparable to all the other terms. right? So this double line notation is very helpful to argue in generalities about the structure of the perturbation theory, but if you literally want to do calculations, you have to be organized, or you have to be very systematic. Still, same methods still work, but you have to be systematic. All right, thank you so much, guys.